Welcome back to OmniEyes, where we explore the hidden wonders of nature and the incredible technology inspired by them. Have you ever watched a massive swarm of locusts flying through the sky and wondered how they avoid crashing together? Millions of these tiny insects navigate tight spaces at incredibly high speeds. Yet airborne collisions are exceptionally rare and unusual. This flawless navigation system has completely baffled scientists and engineers for decades, prompting deep research into their tiny insect brains. Meanwhile, human engineers have spent billions developing complex automotive safety systems to prevent tragic accidents on our modern city streets. What if the ultimate solution to automotive safety was already perfected by evolution millions of years ago in tiny insects? Today, we dive into the fascinating world of the locust to uncover the secrets behind their remarkable collision avoidance sensors. Imagine driving down a busy highway where every single car is moving chaotically, without any traffic lights or clear lanes. This is exactly what a locust experiences every single day while navigating through a massive, swirling swarm of its peers. A swarm can contain up to 80 million individuals per square kilometer, creating an environment of extreme chaos and danger. Despite this overwhelming density, they manage to fly at speeds reaching 20 miles per hour without crashing into each other. To understand this incredible feat, we must look closely at the unique biological structure of the sophisticated locust visual system. Unlike humans, who rely on complex binocular vision to judge distance, insects possess compound eyes made of thousands of lenses. These tiny hexagonal lenses capture a very wide field of view, allowing the insect to monitor multiple directions simultaneously, effortlessly. However, their brains are incredibly small, meaning they cannot process heavy, complex, three-dimensional spatial maps like a human does. Instead of calculating exact distances and speeds, the locust relies on a brilliant evolutionary shortcut known as the looming detector. Deep inside their tiny nervous system lies a specialized visual processing unit called the Lobula Giant Movement Detector, or LGMD. This specific neuron is hardwired to do only one highly crucial job: detect objects that are rapidly approaching on collision. When an object moves closer to the locust, its image naturally expands across the surface of the insect's compound eye. The looming detector monitors the speed of this expansion rather than trying to measure the actual distance of the object. If the image expands slowly, the neuron remains relatively quiet, assuming the distant object poses absolutely no immediate collision threat. But if the image suddenly balloons in size, the neuron fires an electrical spike, instantly triggering an emergency escape maneuver. This elegant mechanism is a masterpiece of efficiency, requiring minimal brain power while delivering incredibly fast and reliable survival responses. The locust does not need to know what the object is. It only needs to know that it is approaching. By ignoring irrelevant details like color and texture, the insect achieves reaction times measured in mere fractions of a second. Interestingly, the neural circuit is designed to ignore objects moving sideways across the field of vision, preventing unnecessary false alarms. It only reacts to the specific visual pattern of an expanding dark edge, which perfectly signifies a direct, impending impact. This biological algorithm is so mathematically perfect that scientists have successfully mapped its precise equations using advanced computer modeling software. The equation balances the angular size of the approaching object against its angular velocity to determine the exact collision time. When the mathematical threshold is crossed, the insect's wings automatically adjust, violently changing its flight path to avoid certain death. Now, let us shift our focus from the natural world to the pressing challenges of modern human automotive engineering safety. Every year, millions of traffic accidents occur worldwide, many of which are caused by delayed human reaction times during emergencies. To combat this global crisis, car manufacturers have developed automatic emergency braking systems, commonly known in the industry as AEB. These sophisticated systems use a combination of radar, LiDAR, and high-definition cameras to scan the road ahead for obstacles. When the system detects a stationary car or a crossing pedestrian, it automatically applies the brakes to prevent a crash. However, traditional crash avoidance systems require immense computational power to process the massive amounts of data gathered by various sensors. Computers must identify the object, calculate its distance, determine its speed, and predict its trajectory before making a braking decision. This complex processing takes valuable milliseconds, which can mean the difference between a near miss and a devastating, fatal collision. Furthermore, Heavy rain, thick fog, or blinding sunlight can easily confuse traditional cameras, leading to dangerous system failures or delays. This is exactly where the humble Locust steps in to provide a revolutionary blueprint for the future of autonomous vehicles. Researchers realize that cars do not always need to identify a pedestrian's face or read a stop sign during emergencies. Just like the insect, the vehicle simply needs to know that a large object is rapidly expanding in its path. By mimicking the locust Lobula Giant Movement Detector, engineers have created novel collision sensors that are incredibly fast and efficient. These biomimetic sensors process visual information directly at the hardware level, bypassing the need for heavy, slow central computer processing. Using specialized microchips, the artificial looming detector calculates the expansion rate of pixels in real time, with virtually zero latency. When the pixels expand too quickly, the chip instantly sends a hardwired signal to the brakes, stopping the car immediately. This streamlined approach drastically reduces the time it takes for a vehicle to react to an unexpected highway traffic hazard. Moreover, because the algorithm is so simple, these sensors require significantly less power and space than traditional automotive radar systems. They can be manufactured cheaply and integrated into almost any moving machine, from luxury cars to basic electric city scooters. Scientists at leading universities have even developed nanoscale devices using advanced materials to perfectly replicate the locust's biological neural network. These tiny artificial synapses use photosensitive materials that naturally increase their electrical resistance when exposed to rapidly expanding light. It is a perfect fusion of biology and nanotechnology, creating a completely new paradigm in the field of artificial intelligence. The implications of this breakthrough extend far beyond just passenger cars and highway safety, into the realm of autonomous robotics. Imagine fleets of delivery drones navigating through dense urban environments, dodging buildings, power lines, and other flying objects with ease. Current drone technology struggles with obstacle avoidance because carrying heavy computers and large batteries severely limits their overall flight time. A locust-inspired sensor weighs only a few grams and consumes microscopic amounts of energy, making it the perfect solution. Drones equipped with these sensors could fly safely in tight formations, much like a natural insect swarm moving in harmony. This technology could also revolutionize search and rescue operations in disaster zones, where unpredictable debris poses a constant, deadly threat. Small robotic rovers could quickly navigate through collapsed buildings, instantly reacting to falling rocks or shifting structural beams without hesitation. Even in the vast emptiness of outer space, biomimetic collision avoidance systems could protect expensive satellites from dangerous orbital debris. The simplicity of the locust's natural design proves that sometimes the most effective solutions do not require massive computational power. Nature has spent hundreds of millions of years ruthlessly optimizing these biological systems through the unforgiving process of natural selection. Every unnecessary neural connection was slowly stripped away, leaving only the most vital and efficient pathways required for absolute survival. As human engineers, we are finally learning to swallow our pride and copy the brilliant homework that nature has provided. This field of study, known as biomimicry, is rapidly becoming the driving force behind the next generation of technological innovation. From bullet trains inspired by kingfisher birds to wind turbines mimicking whale flippers, biology offers endless blueprints for human progress. The locust collision sensor is perhaps one of the most elegant examples of translating a biological concept into digital hardware. It challenges our fundamental assumptions about artificial intelligence, showing that true intelligence is sometimes about knowing what information to ignore. By filtering out the noise of the world, the locust focuses entirely on the single most important variable: impending impact. This laser-focused approach allows a creature with a brain the size of a pinhead to outperform modern supercomputers' navigation. Let us examine how these artificial looming detectors perform in real-world testing environments when compared against traditional automotive systems. In controlled laboratory crashes, vehicles equipped with standard radar systems often exhibit a slight delay before engaging the emergency brakes. This delay, usually around 200 milliseconds, occurs while the central processor verifies the radar data against the camera feed. While 200 milliseconds sounds incredibly fast, A car traveling at highway speeds will move nearly 10 meters in that time. Those 10 meters can easily mean the difference between stopping safely and causing a catastrophic, life-altering accident on the road. In contrast, the biomimetic locus sensor triggers the braking mechanism in less than 20 milliseconds, providing a massive safety advantage. Because the sensor directly processes the optical expansion locally, there is absolutely no need to consult the central vehicle computer. The decision to brake is made at the very edge of the network, right inside the camera lens module itself. This edge computing architecture is highly resilient, meaning that even if the car's main computer crashes, the brakes still work. Furthermore, these sensors excel in complex environments where multiple objects are moving simultaneously, such as a crowded urban pedestrian crossing. A standard system might become overwhelmed trying to track every walking person, rolling bicycle, and passing car in the intersection. The locus sensor simply ignores all lateral movement, patiently waiting for the specific visual signature of an object expanding directly. When a careless pedestrian suddenly steps out from behind a parked van, the sensor instantly detects the rapidly expanding shape. The vehicle halts immediately, saving a life thanks to an algorithm perfected by a swarming agricultural pest millions of years ago. It is incredibly poetic that an insect historically known for causing devastating famines is now inspiring technology that saves lives. As we continue to develop fully autonomous self-driving cars, the integration of these fail-safe biological systems becomes critical. Passengers must feel absolute trust that their robotic chauffeurs can handle unpredictable emergencies better than a human driver ever could. Redundancy is key in aviation and automotive safety, and adding a low-cost, high-speed locus sensor provides ultimate backup. If the expensive LiDAR fails or the deep learning neural network gets confused, the simple looming detector will take over. This layered approach to safety ensures that machines can navigate our chaotic world with the same graceful precision as animals. Beyond cars and drones, imagine this technology integrated into wearable devices for the visually impaired to help them navigate safely. A small camera on a pair of glasses could provide haptic feedback, buzzing gently when an obstacle is rapidly approaching. This could empower individuals to walk confidently through crowded city streets without fear of suddenly bumping into unseen hazardous objects. The applications are truly limitless when we open our minds to the incredible engineering solutions hidden within the natural world. We are standing at the dawn of a new technological era, where biology and silicon merge to create smarter machines. The next time you see a humble insect buzzing through the air, take a moment to appreciate its hidden complexity. That tiny creature carries within its DNA the answers to engineering problems that have stumped our brightest human minds completely. By studying the microscopic structures of insect brains, we are unlocking the ultimate secrets of efficient processing and rapid survival. Nature is the greatest laboratory on Earth, running continuous experiments in physics, chemistry, and aerodynamics for billions of long years. Our job is simply to observe, understand, and respectfully borrow these brilliant designs to improve our own modern human technology. The Locust has shown us that true elegance in engineering comes from radical simplicity, not from adding unnecessary computational complexity. Simple, fast, and highly effective. These are the golden standards of survival in the wild and safety on the road. As we look toward a future filled with autonomous machines, we will undoubtedly continue to draw profound inspiration from nature. Thank you for joining us on this deep dive into the fascinating intersection of biological evolution and modern automotive engineering. Stay curious, keep exploring the wonders of the natural world, and we will see you next time on OmniEyes.